Right. Thank you for digesting while you watch this. All right. So I'm going to talk about the cosmic spider web. So the cosmic web is something we've heard a lot about, and actually, as I'm going to briefly say, it's also, in a formal sense, a spider web. The background here is similar to a lot of large-scale structure visualizations of the cosmic web from a simulation. This was done by Ralph Collar. We've seen some of his other visualizations of simulations. This one is I particularly like this type of visualization, which is a bit different than usual because it's done as though it's a structure that's in front of a light. It's like there's some dark stuff instead of in front of that is backlit by something, and so that sort of reinforces the concept of that this is dark matter, but also I'll show some pictures of origami coming up, which roughly look like this. So here the brightest dots here are galaxies. They're the densest parts of this cosmic web. I'm going to go on to. I'm going to try to go on to the next slide. Okay, so that was a visualization of a cosmological simulation. This is a piece of art by an artist named Tomás Saraceno. So he has a huge studio in Berlin with dozens of people, and one thing that he does that he specializes in is in spider art or spider web art. So this is actually something that was constructed by some communal spiders, some social spiders, I think black widows. This is not the typical sort of spider web that you see, like the emoji. This is a fully three-dimensional thing, which has some similarities in structure to the cosmic web. And actually, the spiders kind of pluck the strings to communicate with each other, which is pretty interesting. And here's another work that he made. So here, this is a full room he enlarged one of these webs built by spiders to room size, so that we can become spiders or something. But also he does explicitly point out at least the visual relationship to the cosmic web. This 14 billions refers to the age of the universe. Okay, so this was kind of a visual thing that some people have noticed. And there was a question whether there was anything deeper to that, at least in my mind, that there was a question about that. And indeed, there is a deep relationship, it turns out, a formal relationship, which relates to Johann's talk that we heard before lunch. So I'm going to talk about this concept of a spider web that's an architectural entity, or structural engineering entity. So in engineering, there are concepts of force polygons. If we have a node with a weight on it, and we identify all of the forces on that node, we can make if that node is in equilibrium, if it's not moving, then all of the forces cancel out and they form a closed polygon. And actually, James Clerk Maxwell, of course, he's best known for uniting electricity and magnetism, but also he did some engineering work and founded this field called graphic statics. And he worked out a way to use what's called a dual tessellation to analyze the forces on a truss work of many of these nodes. So here is a truss work that looks sort of like the Eiffel Tower, and there's a dual tessellation. I don't have so just very briefly, a dual tessellation. In a dual tessellation, first of all, a tessellation is a set of sort of tiles that comes from the word tessel, which means tiles. So it's a set of like polygons. That's what the original tessellation is. And the dual to that in the dual, each polygon, each tile becomes a point, and each vertex between the tiles becomes a polygon. So here, well, this blue thing is the original tessellation. That's the what's called the form diagram in structural engineering, and the black thing here is, or the darker one, is what's called the force diagram. In this case, all of the forces acting on each of these threads of the spider web. The force, there's one of these edges for each edge of the form diagram, and this tells you the forces on each of the members. And a prime example of one of these duals is the Voronoi-Delaunay tessellations, which I know a few of you are very familiar with, but probably not everyone. So I won't go deeply into that, but it is a common entity in geometry, in computational geometry, that actually, well, this isn't coming up very well, but this is an example of a structural spider web that I saw just a few days ago at LAX in Los Angeles. You can at least see up here there are a bunch of cells, and those appear to be, at least to my eye, for my fairly trained eye, these appear to be so-called sectional Voronoi cells, which means that there's one of these Voronoi tessellations, and a Voronoi tessellation, very briefly, is a set of cells based on a set of generating points, such that each cell is the set of space that's closest to that generating point. So the section, so I use the word sectional, that means that it's a cross-section through a three-dimensional Voronoi tessellation. And that's actually the most general type of spider web. Okay, so what do I mean by a spider web? Which I realized I didn't really define that. So a spider web is not just a truss work like this. It's a particular type of truss work of beams or threads between nodes, such that all of the tensions or compressions in these edges have the same sign. So, for example, this thing can be constructed and put entirely in tension, such that none of the if we made this out of spider silk, none of those edges would be sagging at all. It would all be entirely taut, or it could be. So what's an example of a non-spider web? So an example is this kind of thing. There's where you have a node here and edges going all in the same half plane. It's kind of obvious that if you pulled this node all in the same direction, this would never be in equilibrium. So that's a non-spider web. If we added an edge here, then it could be a spider web. And a more subtle case where you have more edges is if we took the Eiffel Tower and this is a simplification of it. So in this simplification, I'm imagining building this to be in tension and pulling on with some force. If we tilted the top there to make this, then this thing couldn't be in equilibrium. It would move a little bit. So we can see that maybe intuitively. And this purple thing, which is the form diagram, we can see that it can't be in equilibrium because all of these polygons don't close. Okay, so that was a very quick thing about this field called graphic statics, which happens to have the same geometry, or sorry, these spider webs happen to have the same geometry as as the cosmic web in the adhesion model, which is the topic of our recent paper. So as Johan said, described very well, in this adhesion model, we have a bunch of cells that start out uniformly. And based on the gravitational potential, some of these cells expand in co-moving coordinates, so subtracting off the expansion of the universe. So some of these cells expand in co-moving coordinates, and some of them contract, and eventually some of them sort of disappear from the whole grid. And in those places, these are where the filaments and the nodes of the cosmic web form. And the method of computing this is exactly a sectional Voronoi, also known as a power tessellation, power diagram, which, just like the wall at LAX that I showed, and there's just the set of cosmic webs, of possible cosmic webs, is the same as the set of truss works that can be made to be entirely in tension, which is pretty cool. And so, okay, is this useful besides making that kind of cool statement? Yeah, this could be. So an example of a practical cosmological measurement, or starting to be practical, is shown here. So the key thing, which I didn't have time to go deeply into, the key relationship between this form and force diagram in the spiderweb is a perpendicularity property. So the point is that if we draw lines between centers of voids, so in white here, those should be in reality perpendicular to walls between these voids, the density ridges between voids. And if we do some scaling of one of the axes, then that perpendicularity is corrupted. Okay, so I'm already starting to run out of time. So one thing you might be wondering is how this relationship, how we came to this relationship. It's actually through origami. And there's some work by Robert Lang, who is an origamist. Here are a couple of works that he made. Here are a couple of other origami tessellations. So there are a couple of papers and a textbook that Robert Lang wrote about this correspondence between spiderwebs and origami tessellations. So, okay, you can't see this, but here's an origami tessellation that I made based on the local universe. So here, this node here represents the Milky Way, and this is the nearest big galaxy, Andromeda, and this around here is something that has been called the Council of Giants. Okay, you maybe can see a little bit this truss work here. This is a dream catcher sort of thing that has the same geometry as this. So this is a demonstration of this equality between origami tessellations and spiderwebs. And so I've actually been working on this origami side of things for a while. Here's a very quick movie of what's called a dark matter sheet, which is a concept used in this cold ice code. So what this depicts is an exactly an exactly compensated void in the large-scale structure, and the edges of this void are sort of like a filament, which gets sort of curled up in position, velocity, phase space. So if you flatten, we're kind of used to maybe simple harmonic motion in phase space, which sort of outlines just a circle. So a pendulum is a circle and makes a circular motion in position, velocity, phase space. But if a structure is growing at the same time as it's oscillating, then it makes a spiral sort of structure, and that's what we get in collisionless cold dark matter. But actually, if we didn't have, if we include normal matter, gas in the picture, the centers of these structures would become sort of fuzzy. You wouldn't have this nice spiral structure. That's because normal gas, if you throw patches of gas toward each other, they actually collide and have some kind of randomness, unlike the cold dark matter. which in principle contains all of the initial information. Okay, I'm just going to show a few movies of idealized universes. So this is a set of nodes of sort of halos in a two-dimensional universe outlaid on a regular grid. And it's one thing that's kind of cool about this is that you can see that the structures of each of these nodes are different. And actually, it's the set of neighbors, the arrangement of the neighbors around each node that determines the structure. So you can see there's difference here. This here is sort of an origami crease pattern that you would have to use to fold this thing in 4 dimensions of phase space. And more realistically, this is, of course, we don't think that galaxies are arranged on a regular grid like that. This is a kind of more random universe, a more realistic universe, and like a slice through a 3-dimensional universe. And these places that become folded up are the places in the adhesion model that become the filaments. Okay, so this probably isn't entirely clear. This is also an origami crease pattern that would be required to fold that up. If we view this in phase space, so this is going into the velocity coordinates. We can see this kind of structure, and I have a short movie, so if you could show the full dome thing, that would be good. So in this movie, it's sort of a square that we're viewing. It's as though we're very close to this square, and it has a depth coordinate which is related to the velocity. It's actually the depth coordinate is the component of the velocity that's perpendicular to the line of sight. So so one thing that maybe you can see is along these collapsing structures, you can see the same kind of spiral that I showed before. That's because we're viewing the component of the velocity that's perpendicular to the line of sight. And if you project this down so if you remove that depth coordinate, then you would get, so could you go back to the presentation? Then you would get the end result of this. So this is the same movie as the thing on the right there. So hopefully that came across at some level. Okay, so I think I only have a minute. Yeah. So there are a couple of other things. One that are related to the rest of the conference. There's the idea of entropy. So one thing that's interesting about and Johan kind of alluded to this, or started to allude to this. If we so there's a loss of information that happens in structure formation. So we start off with these patches that collapse to halos or filaments, and the details of the structure within them, at least in the adhesion model, and to some degree in actual structure formation, some of those details are lost. So we could imagine. So here's an initial potential that gives. So forget about all this stuff, but the way that the universe that this becomes is shown in the intersections of this orange line with the green dots, and in particular here's a potential well that becomes a thick line. So that's basically a collapsed structure in a one-dimensional universe. We could imagine putting a little, deepening the potential there, and this would also change the details of where these dots end up, but we would still have the same object here. And so there's a multitude of initial states that give the same final state here, which is a loss of information or a kind of entropy, which I think is interesting to explore. And this is probably could be related to another sort of information loss in Fisher information, which I have no time to talk about, unfortunately. So I'm going to stop there. So so I talked a little bit about how information is lost in collapsed structures when threads of the cosmic spiderweb form. Another thing that I want to close with is an idea about determinism. How much of the structure now is determined by the initial conditions. In this adhesion model thing, it's entirely determined by the initial conditions, but it's interesting to think about at what point everything is determined by the initial conditions. We don't think what's going on in this room is entirely determined by the initial conditions of the universe, but at some point there's a transition there, which I think is interesting to think about. Thank you.
Comments, questions? I thought with your movie, my thought was that there's something for everyone to think about because we need a four-dimensional dome to show.
You're right.
No questions? If not, then let's thank Mark again and move on to the next. Oh, there was one? Sorry. Please.
So, Mark, with respect to your last remark about entropy or info loss and entropy gain in the cosmic web, is that not a matter of resolution? Because when we listen to our galaxy people, you know, the Gaia people, they still find all the streams in the galactic halo. So
Right.
the information of the buildup of the galaxy is still there. Apparently, the information has not been lost.
Right. So it's only in this adhesion model where the halos become points and the filaments become lines that the information is totally lost. The actual situation, so that's kind of treating halo formation as black hole formation, which of course is not true. The reality is somewhere between complete preservation of the initial conditions and that idealization, certainly when gas is involved. And I think that's something that hasn't been thought about very much, exactly where we are in that transition. Or it's been thought about, but it's not resolved.
Final question.
I just wonder, the idea of the determinism, the very last part that you say there, how you go from deterministic basis, I can't see what would cause something to go from being initially deterministic. I would have thought of something as initially deterministic, it must remain deterministic. Can you comment on that?
Yeah, well, so a gap in the determinism is, an example of a loss in determinism is the more random things that happen when patches of gas collide with each other. So if everything is dark matter, and if we could see all of the positions and velocities of dark matter particles, then we could perfectly reconstruct the initial conditions. But because gas is there and stars form, and there are a lot of chaotic processes, there are possibilities for additional randomness to come into the picture. And at small scales that dominates, I guess, but not on large scales.
Okay, let's leave it.